There's a very quick proof that not every function of this kind is Turing computable. And it's just to do with cardinality reasons. So it's just to do with the fact that there are not enough Turing machines. First, who can give me a quick proof that there are as many, or there are at least as many functions of this kind as there are real numbers?
You can consider all the functions that go from the natural numbers to the set 0, 1, and then those are like, the first one is like 0, 0, 0, the next one, like, they're basically just all the binary, infinite length binary strings. And
that's exactly right. So a subclass of these functions, as you pointed out, are the functions that go from natural numbers to the set 0, 1, which are just sequences of zeros and ones with one position in the sequence for each natural number. And that's just the kind of beast that we saw has the same cardinality as real numbers. So since that includes all of these guys, the set of functions of this kind has to be at least as big as the real numbers. OK. And now what about the set of all Turing machines? So can anyone think of a proof that there are only countably many of those? And a crucial observation here is going to be that every Turing machine has a finite program. It has finitely many states. OK, so here's one way to do it. So what I did here is I wrote down a partial list of all possible command lines that a one-state Turing machine could include. And it's just all possible combinations. So this one says, if you're in state 0 and you find a blank, leave a blank, stay put, and stay in state 0. And that one says, if you're in state 0 and find a blank, write a 1, stay put, and go to state 1. And of course, because there is no state 1 in a one-state Turing machine, that means halt. And I basically wrote them all, except that I need one more column of this kind for go left and one for go right. So if I'd written 3 columns like this one, but just varying what the action is, then that would have been an exhaustive list of possible command lines for one-state Turing machines. This, by the way, presupposes that we're working with one symbol in addition to blanks. Otherwise, we would have had to have more combinations about what you can write down and more combinations about what you can find. The crucial observation is that there are just finitely many of these, which means that if you look at all possible one-state Turing machines, there are also going to be finitely many of those, because you know, all you're going to do is to build a one-state Turing machine is pick 2 of those. One that tells you what to do if you're in state 0 and find a blank, and one that tells you what to do if you're in state 0 and find a 1. So that's it. And something similar is going to happen for Turing machines with 2 states. So again, we're going to have a finite list of possible command lines, and you're going to pick 4 from those. You're going to pick, I mean, at most 4. You're going to pick one that tells you what to do if you're in state 0 and find a blank, what to do if you're in state 0, find a 1, what to do if you're state 1, find a 0, a blank, what to do if you're in state 1 and find a 1. And again, you're going to build them from combinations of those. So you're going to have finitely many possible 2-state machines. And similarly for every n. So here's a way of showing that there are countably many in total. We can number them. So we can assign a natural number to each Turing machine. Just let 0 be the first one on our list of 0-state Turing machines, and count them all until we get to some number k. And then let k plus 1 be the first of your 1-state Turing machines, and count them all until we get to some number j. And then let j plus 1 be the first of your 2-state Turing machines, and so forth. And every Turing machine is going to be assigned some natural number. So there are as many Turing machines as natural numbers. So we know that there are functions that are not Turing computable. And here's what's exciting about this. As I pointed out last time, there are the functions that are Turing computable are exactly the same ones that are computable by an ordinary computer. Indeed, an ordinary computer with unlimited memory. So that means that there are functions that no computer of the kind we know and love could possibly compute. And you know, that is a very deep fact about computers. They're limited in this essential way. And notice that that's in spite of the fact that we're not here talking about efficiency. So we haven't talked about functions that could be computed quickly. Like, things are going to get much worse if we do that. Here's just things that can be computable simpliciter.